Y'all, what's up? Coach Hyde, dripped out Monticello Hurricanes gear. Got a video for you, log conservation of mass. So I know it's been a little confusing, but you just got to think of it at its simplest form. All right, log conservation of mass. To conserve means to maintain, protect, something like that, right? So we're just trying to make sure the mass is protected, that it's not destroyed. We're not taking away any mass. We're not adding any mass. The mass is the same before and after a chemical reaction. Right, so this is a chemical reaction. This arrow sign here is the yield sign. That's what it's called, right? It's like the equal sign. This is where the reaction actually takes place. All right, so during this sample, it's just a very little piece of this equation. That's where the reaction is actually happening. Nothing is happening here. Nothing is happening over here either. That's just the before. Before the reaction, this is what you got. It's like where you mix in all the ingredients for the pie, right? This is where you're actually like cooking the pie in the oven, making the pie become the pie. And then this is after you pull it out of the oven, you have the pie, right? Don't know where the pie reference came from, just came up with that just now, but I like it. I think it's pretty good. So you have the before, okay? The before the reaction, this is called the reactions. They come together and they react together, things like that. This is where the reaction is actually occurring. Then over here, this is after the reaction. This is the product. Right. All this law of conservation of mass, the only purpose of this thing, the only really reason we're dealing with it is because we just got to make sure it's equal, right? There's got to be equal amount of mass before as there is after. That's it. That's the whole purpose, all right? Because we cannot create matter, we cannot destroy matter, right? Not since like Big Bang expansion, all that crazy stuff happened. So anyway, let's just talk about the atoms first, okay? So if we look, we have atoms. We have hydrogen, okay? Now hydrogen naturally exists bonded together with other hydrogens. So if I was to draw a picture of this hydrogen, right, it's H2, right? So I would have two H's bonded together. Because they're both hydrogens, they're the same element. It's not a mixture of different elements, right? It's two elements. This is a molecule, right? That's a molecule of hydrogen, hydrogen gas. The G means the gas, right? Here's oxygen. This is O2, right? There's two oxygens bonded together. So if we were to draw a picture of this, oxygen is going to be bigger, right? Kind of looks like a set of eyeballs or something weird like that, don't it? But that would be a molecule of oxygen. It is also in the gas form. Right? So then we have the reaction takes place here. I'm going to draw a line through this. This just separates the before, the after, because this is the middle. This is where the reaction is happening. Now let's draw a picture of this. All right, so this has more than one element. This has hydrogens and oxygens. It's in the liquid form. The L means liquid. So this is not a molecule because it's not just two hydrogens or just two oxygens or whatever. This is a compound. All right, so we have molecules that are two elements or more bonded together that are the same element. Then we have compounds, which are a mixture of two or more elements bonded together. All right, so now law of conservation of mass says there must be equal amounts before as there are after. All right, so over here, right, I have two hydrogens. This is just making a little list to kind of keep up with it so I don't forget what I'm talking about. This is two oxygens. Now over here, I have two hydrogens, but I have one oxygen. So the problem is this doesn't match up. This is not law of conservation of mass. Okay, so 2 and 2 is good. I have two hydrogens on both sides. That is conserved. That's what we want. But I have two oxygens and one oxygen, and that's not what we want. They don't match. They don't balance. That does not support the conservation of mass. So that's when these numbers come in here. All right, these are coefficients. You could put a coefficient in front of the number, right? So what this does, this 2 means I have two hydrogen molecules. So I don't just have one of these, I have two of these. Okay. So I actually have a total of 4 hydrogens over here. Now there's no coefficient here, but just like in math when you have an x, if there's no coefficient in front of the x, you assume that it is a 1. So I only have one O2 molecule. So I have 2 total oxygens. Let me fill it that. Okay. Now over here, I have another coefficient of 2, which means I have 2 of these water compounds. So I have 1, 2, 3, 4 total hydrogens, 1, 2 total oxygens. So by using these coefficients, this has balanced the equation. This has made the law of conservation of mass true. Right? If I got 4 hydrogens on this side, they can be rearranged differently. Right? They don't look the same, but I still have 4 over there. I have 2 oxygens here. I still have 2 oxygens over there. That's what law of conservation of mass is all about. We want them to be equal on both sides, before and after. If they're not equal, conservation of mass does not hold true. The way we can look at this is with an actual mass number. Remember, we measure mass in grams. So let's say I have 10 grams of hydrogen that reacts with 20 grams of oxygen. Law of conservation of mass says there must be equal amounts of mass over here. There's 30 total grams over here. 10 plus 20, 30 total grams. When I say here, here's where the reaction happens. So the reactants, before there's 30. So there must be 30 over here. There's only one thing over here, right? Water. So there must be 30 grams of water. All right, another way you might be asked to kind of figure this out is, what if I told you we had 5 grams of hydrogen and 25 grams of water? How much oxygen must have been used? Well, conservation of mass says equal, right? Equal. So over here, there's only 25 total grams. Over here, we got 5. So how much oxygen must there have been if we need 25 total, right? Because we need 25 on both sides. So how much oxygen must have been used to make it 25? 20 grams. All right, to start making a little more sense, all you're doing is just making sure both sides are equal. And you're either making it equal by making sure the grams are equal, or the amount of H's and O's and E's and all those are equal, right? So you're making the atoms equal or the mass equal. So let me give you one more example. Let's do so this is an acid-base reaction. You don't really need to know that, but if you remember from last unit, we have the OH in the compound, the hydroxide with a metal, so that's a base. And this is hydrochloric acid with the H right here up front. So we can balance this out, but if you want to do that, check the video on balancing. Just want to show you one with 4. So we have 2 here in the reactants. This separates our reactants from our products. We have 2 things in the products over here. So I just want to show you with 4 instead of 3. We can say something like, all right, this is probably heavier, so we'll say that's got 5. Can't see that, can you? 5 kilograms of magnesium hydroxide react with 2 kilograms hydrochloric acid. So this is our reactant. This is mixing the ingredients together for the pie. Here is the actual reaction, the actual cooking of the pie, right? Actually, the things going on. Then the after, right? Let's say after, I'll just say, 4 kilograms of water. Can't see that, can you? 4 kilograms of water. I want to know how much magnesium chloride is there. Conservation of mass, right? Must be equal amounts of mass over here as there is over here. We have a total 7 kilograms of mass in the reactants. So we must have a total of 7 kilograms in the products. 7 and 7, right? 7 equals 7. So how much must be here for this to be true? Well, you got 4, so 4 plus what equals 7? 3 kilograms. All right, so that's it. That's basically all we got to know about law of conservation of mass. Is just we can't create it, we can't destroy it. So that means that there must be the same amount, right? If this was not the same, right? So if this was 2, if we only had 2 kilograms, then our total over here would be 6. So our totals would not be the same, which would mean somehow, some way, we have destroyed 1 kilogram of mass. And we know that that cannot happen, right? The mass can change from the way it appears before to the way it appears after, but it's not going to disappear altogether. Or, if this was 4, now we have gained mass somehow, so we've created it out of nothing. And we know that's not going to happen. So that's what we're trying to ensure here, that everything is equal before and after the process, right? Here's the process, here's the reaction. So hope that works to clarify what you're trying to figure out with your law of conservation of mass. Got several videos on balancing. Okay, when I say balancing, this is not balanced. Right? So if we were to count atoms, it might be balanced. I don't know, I just made this up off the top of my head. Let's see. So in the reactants here, I have 1 magnesium, right? We'll distribute this, right? So I'll have 1, 2, 3 hydrogens, 2 oxygens, 1 chlorine. So this is my total number of atoms in the reactants. In my products, I have 1 magnesium, I got 2 hydrogens, 1 oxygen, and 2 chlorines. So see, the only thing that matches, the only thing that's balanced is my magnesiums, right? So this is an unbalanced equation. This is not true. We do not have equal amounts of atoms in the reactants as we do the products. We would have to balance this. And I got about 3 or 4 videos about actually balancing it, right? And what that means is you're going to insert numbers here, and with the purpose of making there be equal amounts of atoms on this side as there are on this side. So check those videos out as you work your way into that, but that's the next step of what we got to do. All right, see y'all later.